So let's say I've got that Etsy password file, right? And I said that if you want to change your file, or let me. I just copy it to my file. So I don't change my password file.
Yeah.
So I say cat my file. And the thing is with sed, if you want to replace something, like you can say sed -s, say Meffie to fix the spelling to Meffie. That. You can see that it changed that line. So the question is, how do I change that? If I want to change that file, the typical way to do that is say it's my file. I would say move it my file to my file.temp, and then you say cat my file temp sed that, and then I put it back to the original name like that.
Okay.
So that's how typically you do seds. You can't change that file in place, but you can. I lied. There's an option called in place.
Okay.
To change the file in place like this, you say sed-i for in place, and then you say the name of the extensions, because it'll create a backup of that file.
Okay.
So you can say dot bash.
Which is nice.
And then you say
So that basically just automates that workflow right there.
yes. So it'll change my file in place. If I look at that, it changed it to mfood here.
Yeah.
And it created the .back file. And the reason I found that was because I needed to change a file, and I was like moving things around like that. And like, I know Perl has this option to do that, and I looked at the man page actually. I wrote down and read the document. So there's an in-place option for sed. And the task that I had was actually so the task actually was when you set up. You guys know what Django is? It's a web framework.
Yep. Yeah.
So yes, in your Django settings, there's a settings file. You got to set this thing called secret key. You have to set that value to some unique number. And so Django has this way of setting the initial one when you're setting up the project, but later when you deploy it, you've got to update it to be something unique on the server. And there are people that wrote utilities that web-based utilities. It's like key generator.
Yeah.
But I had a couple problems with that. One is I'm generating a key on someone else's server. I didn't like that idea.
Yeah.
And two was I had to do it through a command line. I didn't want to have to access a remote server. So I thought, okay, well, I'll just generate a secret string or a random string and put it in there. So how hard could that be? So after a little bit of time, I thought I kind of tried a couple different variations, and it came down to like, well, there's this thing called there's a pseudo device called random. There's one called random and one called urandom.
Okay, yeah.
Urandom is the non-blocking. And this will generate some random bits. And I'll just pipe it through here to show. So it just generates random noise. So I thought, oh, that's easy. I'll just grab that and make a key out of that. So I said cat dev random. And then, well, let me clear this. cat dev view random. But the thing is, I only want printable characters. I don't want.
Right. Has to be.
Has
Does it have to be
has
just
to be a string.
ASCII or?
Has to be ASCII.
Okay.
Yeah, in that string. So, what I came upon was this thing called TR, which TR will transliterate. So one of the things you can do with TR is, like the typical thing you do with TR is say, like, I want to take all lowercase letters and make them into uppercase letters. So something like that. It transposes characters. But you can also do something like this. You can say -D, and that will delete characters. So what I want to do here is I want to delete all non-printable characters from the stream. But there's not an easy way to say non-printables, but there is a way you can say printable characters. So you can say -C, which is the complement. So I can say I take a complement of printable characters, which is AZ09. So now this says, give me a stream of random characters, delete the characters unless they're in the set AZ09. So now I get a stream of characters. But I only need a string, so I need to chop it off. So then I had to think about how to do this. My first idea was, well, I just use sed, and I grab a certain amount, and I had this huge real expression. And then I realized, you can use head to grab like a certain number of lines.
Yeah.
But there's actually an option to say Z, or give me a certain number of characters. I can say, just give me 40 characters. And there you go. There's your random string.
Nice.
All
So
right.
now, coupled with the set in place, the command is, this is the command to get the string. So I can say key, and I can put that into a variable. And then I can say sed -I back. It's the secret key I'm going to replace. It starts at the beginning of the string. So I'll replace everything with secret key. Oh, and this is supposed to be a. And because this is a double quote here, this will expand out to that value. And then I can do from that place. So that's my 2 lines. For that 2 lines, then I just drop into a script, and that's now I update my.
And that's the thing I love about the command line.
So there's the secret key. So that was that. That's why I needed the in place.
Yeah.
Hey, Scott.
Hey.
We were just talking about sed because I lied last week. So I had to clear the air. Did you get that, Stephen? If you're watching in the future? All right.
Meffie Stoffoli has made a mistake.
It happened.
I'm shocked. Shocked, I see.
It wasn't really a mistake. I was just seeing if you guys were paying attention.
Ah, I see.
So, well, tonight we're supposed to be talking about debugging, right? That was the topic of. So I thought what I do is I put together some slides here talking about some different debugging tools on Linux, just to give some background. So these are what I call tools of the trade.
I knew S-Trace would be in there.
Yes, that's trace. That's only because we don't have trust. So starting with Bash. Oh, Scott, did you upgrade Bash on our servers today? Did you see the security issue on Bash?
A remote exploit?
Yeah.
On Bash? How do people even get to it to exploit it remotely?
It's used, well, if it's used for CGI, it's used for SSH, it's used for a bunch of things.
Oh, okay. I don't think we have any.
DHCP uses Bash. So what you can do in Bash, the security exploit that was announced today was that you can inject Bash code into the environment that invokes Bash, and then Bash will run it.
Oh, lovely. Well, we don't expose DHCP, and nothing that we have, as far as I know, uses CGI.
Not anymore.
RT doesn't. It uses Pro.
So yeah, there's a Bash exploit. So
Oh, lovely.
yeah, code injection exploit. So Bash. So are you guys familiar with bash-x? You know this option?
To debug bash, yeah, like I've used it a little bit.
Yeah. So this is really handy when you're trying to debug your bash scripts. It just basically prints all the commands that go by and so you run the script like that, you can get that bash-x, whoops, with the space, sorry. You get a little plus in front of each thing, let me throw that in here. So you get a plus in front of each thing, and you get like some tracing. Well, another kind of handy thing to do in Bash. So sometimes you put comments in like this, right?
Mm-hmm.
As you're making progress. But if you can actually do this instead, and that's actually a bash null option. So like the null, don't do anything character. So it doesn't change the script, but since it's an operation, it actually shows up on tracing. So it's like comments that can be traced.
So what was that originally intended for?
You can do things like this. So it's a placeholder. It's a no op.
Okay.
So because
Guys, what
you can put this in a number of places where you have to have a placeholder operation, but you don't have to do anything.
Yeah.
Another handy thing for this is something like put in documentation. Normally this string would get pushed into that, but it's getting pushed to the no op. So that's a bit of bash debugging. Go ahead and see those strace.
saw your presentation last year at the meeting, but I don't use it every day, so.
Oh, okay. So
Know about it, but know about it, yes, know it, no.
So S-trace, Paul Ferris actually was the guy that showed me S-trace a long time ago, but S-trace is like on Slur, so you have something called truss.
Okay.
And S-trace is a tool to trace system calls in a program. So it's like looking under the hood of what a program is actually doing. So you can so the normal way to run it is like say, clear this. The normal way to run it is say S-trace, and then the program you want to run, say S-trace ls.
Okay.
And it shows you everything that ls does. It's kind of chopped off on the side there. Is that better?
Yeah, it's probably better.
So, and it prints stuff to standard error. And there's a lot of options to it. You can output to a file instead of standard error. So I can say clear, say S-trace, output some file. A lot of times I do this. Temp, ls, S-trace. So I'm going to run S-trace and it's going to trace output. It's going to put it into ls S-trace in the temp directory. Every system call ls made. And it shows you there's a lot of stuff that happens on the covers. It shows you every system call, the options past that call, and the return code. A lot of stuff. So in this case, it loaded all the DLLs or the shared objects we're using, and then right down here, see, it does. We're doing open on the current directory.
Yeah, right about there's where SA Linux faults you out.
And then here it says right here, get directory entries. So we're getting the directory entries of the current directory. So we've got 3 entries, which are the file, parent, and the current directory.
Okay.
And then it pulls that. And then it got the entries, and then it stated them. It stated the file. And that's to colorize the file. To colorize the output. And then we wrote right here, see, when we saw that printed to the screen, this is what it printed. This is the right command that printed that to the screen. And this is the file descriptor. So 1 is standard out.
Where did on this, it's like equals 9 there in that line.
There?
There's an equal sign and
To your right.
to your right there. And the same line is right.
That vertically aligned
equals
column is
9?
yeah.
Thinking that's what right returned. So that'd be 9 characters probably. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
This is the number of characters written. Yeah, it's enclosed, return 0. Exit doesn't return anything. So this is a really cool program. I'll give an example. Say like, when things are going wrong, or let's say, actually there's this is probably a bad example because so if I say man grep, it opens a man page for grep. Where's the man page? So I found out later that there's actually a man has an option to show you where where it finds it. But before I knew that option, this is how I would have. I can say, you can say strace. It's first it's opening these SOs. These are shared libraries that needs to use.
Oh, okay.
But here, now we're starting to health stat. So we're trying to stat. So we're looking for. First we look at user share man one grep. And it looks like it's statted all though. Yeah. Yeah, so that's I found it right there. If you have a program that is like looking for a file in different directories, for example, it will show you every directory it tries. So if you have something that's like looking for a file and then it fails because it can't find it anywhere, you're like, well, where's it supposed to be? You can run strace and it'll show you every place it's looking for that file. And you say, well, I'm supposed to put the config file in this directory. Stuff like that. It also does, for networking, it'll show you like the system calls for moving bytes of the network. How many bytes you send, who you send it to, which IP address. So I could do like, I can do wget. What's the name of a website? Does anyone know any?
Google.com.
The Google. .com. So wget is a command line program to get a web page. Right, it created that. It got the index of Google there and saved it to a file. Prove that. I'll do it again, but I'll run it through strace. Shared objects. So opening shared objects. Shows me every shared library that my program's loaded. For some reason, we open this file, locale archive. Oh, we're statting.
Right to the.
So when I run wget, it always opens this file. Or tries to open this file. It shows that I open this file wget.rc. Apparently I have that file. And this is the file descriptor it opened. So like anytime you see reads and recs against 3, we know that that's the file. It opened it as read only though, so it's only reading from that file. Oh, so this is the read commands. This is what is in that file, that big file. And now we're looking for one in my home directory. A dot wget.rc. And returns email. There's no, I don't have such a config file. So now I know if I put a dot wget.rc, it also brings that one.
I've noticed that convention before. Like the home directory file will always have a dot before it, but
Yes.
the global will not.
Yes, yeah, it's usually, if the dot is a hack to make it hidden.
Right.
Yes,
As an
because
aside, that was an error, actually.
if you want to let users create a configuration file for an application, you should certainly make sure that file is hidden from them so they won't know it's there.
Yeah. Well, do you know why? Do you know why they have a dot? Do you know why they have a dot in front of them?
Presumably because the original versions of UFS way back in the day couldn't really support hidden files.
No, they didn't support hidden files. When you run ls, normally it doesn't show the dot.
Yeah, unless you
It
put
doesn't
that
show
in.
the dot directory. Unless you do the -a. The way that was coded was when they originally wrote Unix at Bell Labs, the programmer was lazy. He just says, if the first character is a dot, then it must be either the parent directory or the current directory, so don't show it.
Nice.
And then later on, people realized, if I make the first character of my file a dot, ls ignores it. So it was really a bug.
So this is actually not
When people started, and it wasn't a feature. No, it was not a
this is
feature.
anthropology then.
It was not a feature. It was just like, this is how people started using it. I was like, oh, okay. And so now, but then it came entrenched, and they couldn't change it.
Mixed anthropology.
Clever.
I don't mind the fact that the dot represents a hidden file. I mind the fact that, for example, wget would expect its config to be hidden. There ought to be, tilde/etc should be reserved just like /etc is for the system. Tilde/etc should be where your configuration files go for the user, and then everything should be unhidden in there.
You would think, but no.
But then how would you hide the htaccess file?
Science.
Well, anyway, at some point we're going to actually. Oh, so yeah, we're trying to look up Google. We do here's the bind. So here's the socket stuff finally. Actually, this is. I think this is the DNS lookup. See, because it's netlink, just family. So here's we're sending packets over the network here. Receive message. We're sending a packet. So this is probably I think this is the DNS lookup for Google. See right here, resolving the name. That's the DNS lookup.
Is AF Netlink your virtual adapter for your virtual machine?
No, that's the socket family.
Oh.
So that's just the DNS lookup uses that family. It's not TCP. You don't use TCP for the DNS lookup because you have to have the address before you can do TCP. You go down here. Eventually, we're going to get to it. Oh, we're still doing the DNS lookup. Oh, here it is. I lost it again. I lost it. Where is it? Here's INET. This is actually where we're doing the DNS lookup. Okay, so. See this one right here? AFS INET means IPv4. So we're going to do open an IPv4 socket,
And do you know what AF stands for?
address family.
Abercrombie and Fitch. What would it be if it were IPv6?
AF INET 6.
Makes sense.
And okay, so here's where we write to the screen, connecting to Google.
Well, so what's
Here's support 80 right here. I'm sorry?
PF INET?
PF INET is just a protocol family.
Okay.
It actually has the same value as AF INET. They made them two separate things just in case someday they change their mind. But it's essentially the same thing. So this is actually so these are the system calls that wget is doing to actually connect, create the socket, to connect to port 80, and here's the address that we're connecting to, which is the IP address of the Google server we found. So we open the socket, and here's the HTTP request that we sent, get/HTTP1 user at patient. So there's this big string here, it's 114 characters. We send it, and we start receiving data, and then we're reading what Google sent back to us. And then the stuff at the top of index.html. See how easy that is? So yeah, you can see all the details of what's going on. So 9 times out of 10, that's getting you through the day. So now GDB. So you guys know GDB, right?
It's the GNU debugger.
Yeah, GDB is a GNU debugger. So this is more like when you're programming, right? For native applications, you can use it to debug your programs. You can use it to debug programs you're developing, or to debug programs that are already deployed and have crashed, and you can get a core file from a user. So my slides didn't render quite correctly. The code here just supposed to be this is supposed to be like a code font, but anyway. So these are like the commands you use in GDB. It started as like interactive, and it's there are GUI front ends to it, but I don't use them. There's just a command line interface to it. You set like breakpoints in your code, and then you can step through your code. You can print variables, things like that. And you can, if a program crashes, and you have your system configured to allow it to leave what's called a core file. Are you familiar with a core file?
Core dump.
Core dump, yeah. Of course, that was called core because the computer members used to have cores, like magnetic cores in them. So that's where the name comes from. Or you can actually attach a running process. So if you know the process ID and you have permissions, you can attach to that process that's running and step through the program. To test for memory leak and buffer overflows. This is an extremely handy tool. And then finally, there's a tool for debugging the actual kernel itself. All the stuff I talked about before is all user space stuff, but when you're actually debugging the kernel, that's an entirely different system, right? You need a kernel level debugger for that. So there's this tool called Crash. So if actually Linux actually crashes, you can get it to create a kind of core file for the whole system. It uses a thing called a VM core, which can be extremely large because it's basically a snapshot of the entire memory of the system. And then there's this program called Crash that can decipher that. You can print all the data structures that were in the kernel, and all the stacks. Look, it's AFS. It works.
Well, for the moment, yeah.
Till you get on it, you'll fix that problem.
No, it's working. Yeah, see? Good cat. So this is a little program. GDB. So this is what looks like when you start it. L is to list.
Mm-hmm.
Instead of breakpoint, instead of breakpoint, main. I run my program and it stops. So I can print variables. Next. Next. That's basically how. Of course, there's a million things you can do with it, but that's the gist of it. You can inspect your variables, you can set things, change things. One other thing you can do is this is very useful. BT is backtrace, so you can see how many functions teachers nested in.
Mm-hmm.
That's my World War Tour of debuggers. Did you get all that, Stephen? Is there any, do you guys have any questions about that stuff? I didn't talk about like Python debuggers or anything like that, or Perl debuggers, but
Can you use GDB on C++ applications?
yes.
Same way?
I haven't though. Yeah, so here's shows an example.
I've heard of many programmers that think they do not need a debugger.
That might sound silly. Well, another thing that's interesting with the debugger is I think it's interesting.
Isn't that what customers are for?
actually show the object code of you can disassemble the object. There's different ways. You don't have to use GDB to do this. There's other ways to do this too, but this is one way you can show the object code. So this shows the actual. This is the actual Intel commands that are run. So when you compile your C program, this is what it actually generates.
These are the assembly.
That's the
code.
assembly that the C code generates.
Push, move, subtract, more moves, exclusive or, compare along, jump if equal.
So like this exclusive word is just to reset the
Yeah, that's
It's like
sensitive
zero.
to all zeros. They
This is
do
just
that,
all
they do
set
that
up.
with an XOR because it avoids having the constant zero take up a byte of RAM,
yes.
which probably doesn't matter all that much anymore, but back in the days when I was getting my start, you did stuff like that because saving 1 byte of RAM was a big deal. I got my start on an 8080.
Yeah, it's a single opcode, so
I remember those.
Yeah, that used to be a single byte opcode.
oh, and this actually brings us into a segue. Boolean function. That's what I call it.
Mm-hmm.
That's the name I call it. This segue is, since we're talking about debuggers, I thought it'd be interesting to talk about buffer overflows,
Mm-hmm.
because that's a type of bug that's an insidious bug that
People like to use.
people, you hear about a lot. So it's like, what is this buffer overflow business, right? Are you guys familiar with buffer overflows?
Mm-hmm. Not professionally, because we use managed languages, right?
Hopefully.
Yeah. It'd be real bad if we came across one.
Yeah.
Some of what I see, I wonder, but
Yeah. So this is the limit of my artistic abilities. This little sketch here. So to talk about to understand buffer overflows, the first thing you need to understand is a bit about. Well, first I should say buffer overflows on modern systems are really hard to exploit, right? Because modern systems have safeguards to prevent them, but they're still not 100. You're still not 100% guaranteed to avoid it.
Yeah.
But just stepping back on how, like traditionally, what happens is when your program is loaded into memory, you have a code segment, and then you have data, and you have a segment that's called a stack segment. It's a stack region. And you have, in your registers, you have an instruction pointer, which is the code that's being executed. So this points to the next operation.
mm-hmm.
And so this is stepping through the code. I mean, it's incrementing. And then it comes to, unless it comes to a jump, and then it moves it,
Mm-hmm.
or a call. If it's a call, then it'll be a jump to a location, but we save where we're going to go back to on the stack.
Mm-hmm.
In this data region down here. And then we have this thing called a stack pointer. This goes up as we call functions. We save our address to return to on this stack. So this is a von Neumann architecture. Is that right, Scott?
Say it again.
It's von Neumann. It's a von Neumann
Von
architecture.
Neumann.
Von Neumann.
Neumann.
Von Neumann architecture, because what happens is you have one memory region for data and code. There's no distinction. And the reason is that originally computers actually had code that would generate code at runtime. It was modifying the code that was using. We try not to do that nowadays. But the hackers still like that to do that. So the trick here is, what you want to do is, the stack region has the return address, but the stack region is also used for temporary variables and functions. Because the functions have local variables, they have to put that data somewhere, so it's put into the stack. So the trick here is to try to commandeer the instruction pointer. So what you do is you want to put some opcodes in the stack that you can use to take over the program, and then try to get the instruction pointer to point to your code. Since the local variables are going in here, and the place we return to is also going into here, you can see an opportunity to corrupt it so that you can take over the instruction pointer. And that is the gist of what's called stack smash.
Scott,
Yes, sir.
who is von Neumann?
Von Neumann was one of the early computer scientists. He was European. I don't remember specifically which country he was from. It was
He's from the U.S.
maybe his name is pronounced the European way though. So he was like of Dutch descent. I can hang on a second. I'll Google him.
Well, he was at Princeton, I thought.
He may have been. Let me Google.
But I don't know. Yeah, I don't know what his nationality is. So here's a close-up of
John von Neumann, Hungarian.
Hungarian. Okay.
He was Hungarian and American. Born December 28th, 1903, died in 1957. And he was looking for the von Neumann architecture. Basically, he came up with the idea of fetching an instruction from memory and executing it, and the separation of instruction stream and data stream. The notion of having an instruction pointer and fetching the next instruction and controlling logic flow by an instruction pointer, that was his origin. Believe it or not, although we take for granted that that's pretty much the only way you can build a computer, it turns out that's actually not the only way you can build a computer, and it's just the way that has been adopted almost universally. But some of the early designs, they did things like data flow architectures where they were looking at different ways to do it. Some of the non-von Neumann architectures are actually more parallelizable than the von Neumann architectures, but it turns out economically von Neumann is usually the choice because it's cheaper to implement in most cases. Requires less hardware gates on silicon to do the same amount of processing, and we basically have just thrown sand at the problem. We haven't really, except for a few specialized situations, we haven't really tried to build massively parallel hardware down at the deepest levels of the machine. We do parallelize at the software level and the compiler level. We have hyper-threading and multi-core processors, but the quantum computing that's under development now takes that to a whole new level, and those are not necessarily von Neumann architecture. So there are actually different ways of approaching the fundamentals of computer science, and he was the one who came up with the one that happens to be the one we use the most.
World War II-ish?
Yeah, pretty much.
Well, a while ago.
You guys have built any that had to disagree with that.
I know him from the
There's-
self-replicating machine idea.
Yeah.
Yes, World War II, because he was working on the Manhattan Project.
Oh, yeah, a little project that kind of went nowhere.
Yeah,
Yeah.
sort of blew up in everybody's face.
But
So this is more details here. So here's our memory region again.
Okay.
So on
Yeah,
my-
his contribution, according to Wikipedia, his architecture, officially the definition of it, was that you programmed it by storing the program in memory and fetching it with an instruction pointer. The early computers before that, you actually rewired the circuitry to do the computation you wanted.
Yeah.
So he came up with the idea of storing the program independently of the circuitry.
Pretty pretty revolutionary idea.
I would say.
Well, actually, Turing thought of it because von Neumann recognized what they were building was a Turing machine. So,
Yeah.
but yeah, it's really fascinating. So the thing is, in the modern systems, this area of memory is actually the kernel marks this as executable, and this is not executable memory. It actually you can actually, like on a primitive computer, it was all just memory, data and code all intermixed. There was no distinction between them. But as the hackers got better, we had to be more careful about it. Because in original computers, the code itself was actually being generated as the program progressed. It was not just storing the opcodes, but we generated the opcodes. So the programs were self-generating. But anyway,
Which makes sense with von Neumann.
yeah, because before that time, like I said, before that time, they actually had to hardwire things.
Yeah.
And of course, you know, on primitive computers, they only had like a couple hundred bytes to deal with, right? So, like I was reading the other day, it's like the original version of Linux kernel fit in like 1K or something ridiculously small. It's like smaller than your email headers these days. So, so here's the stack frame. This is like a picture of the stack frames. So like here's an example program. I've got a function. Is that big enough? I don't know if you guys can see
I can.
that.
Yeah, we can see it.
Probably zoom in a bit. Maybe I can't.
It looks fine, honestly. You can read it. Oh, whoa.
Something like that. Okay, so anyway, so here's, you can see, so we got this foo and it calls bar. And then bar does some stuff and then returns. When bar returns, it's got to come back up to where it was inside of foo. So, if I zoomed in too far, didn't I? So the thing is, so what happens is, when we jump into bar, we have to store these local variables somewhere. We store them on the stack. So in this case, for example, I put in 214 into this area of memory, and then I've got 6 bytes here, and I store 1, 2, 3, 4, and a couple of null characters into here. And then after all that is a memory address of where I'm going to go back to. So this is like, actually, it wouldn't be 1,000. It'd be 1,000 plus some numbers because I'm going to jump back into right after bar. Right? Because this is not a permanent marker. Yeah, because the code. What happens is the instruction pointer points to here. We run these instructions, and then the instruction pointer goes down, jumps to here, and then we run these instructions in bar. And then the instruction pointer has to go back up to where it was after the call. Because there's a call here. So after the call, it's got to go to here. So it's going to be like whatever that number is. So here's the trick. The trick is, if I'm getting this right here, it just shows like I'm assigning it from memory here. But if I'm getting data from outside the program and I'm stuffing it into this character buffer and I'm not careful, I can make that too long. It dribbles over this area of memory. And I can dribble over all of these too. And if I dribble over that area of memory, I can set that to some number, which gets set to the function, to my address, my instruction pointer. So I can dribble memory into that and push it into the register, the address register. So I commandeer the instruction pointer. And I can point to maybe something down here, which is my evil code, and then that code runs. And that code could be something like,
Erase your hard drive.
yeah, erase your hard drive. It
Or-
could be start a shell, so I can do anything.
Yeah.
That's what it usually would be. So typically, this code here is called shell code, because what it will do is start a shell, and then from that shell I can run any command as that user
That's why they call it arbitrary code.
Yes, arbitrary code. It's called shell code. So, as an example, here's this stupid simple example. I'm not going to actually take over the computer, but so here's my unsafe function, I called it. And down here is main. And so what this does is it takes an argument. So here's the usage for this. I say overflow string. And I take the string that I pass in and I pass it into something called unsafe function. And then I return. That's all we do. An unsafe function takes a pointer to memory, which is a pointer to the thing that I passed in. And I do this thing called string copy. And string copy takes those bytes and copies them into a buffer. It's only 10 large. And string copy goes until it gets to the first 0 character, the first null character. And it doesn't care how big buffer is at all. It doesn't know how big buffer is. So what happens is, if the string is too large, if input is too large, and then we clobber our stack frame. Let's see what happens. So first up, Nate actually just builds it, so that's already done. So I'll say overflow A. Oh, okay, we're good. AB. How many characters am I up to? So what's happening here is I'm overflowing that buffer every time, but just enough that I can get away with it. Well, I'm getting tired of doing that. Oh, here we go. So, so what this is, stack smashing detected. What's that?
Over on the whiteboard there.
Oh, okay. So this is one of the protections I told you about. So in modern systems, we have this thing called, so this idea of overwriting the return code is an attack called stack smashing. Okay. And so what happens here is the compiler, modern compilers have this option to, what they do is they put like a sentinel value around the stack frame. And they see like, what happens is if I overwrite that sentinel value, that, oh dear Lord, someone overwrote the stack, and so things are corrupted, they're trying to smash the stack. And so instead of trying to run the shell code, it just stops the program. And it just faults the program, and then it dumps it into a core so that you can try to figure out what happened.
So the trick then for the black hat programmers is to get the overflow the buffer without smashing the stack and triggering that
Yeah.
overwrite.
Just enough. It gets harder and harder, but yeah, it's still possible. And also you can turn the stack smashing off. So if I do DDV, you gotta do help. Core. Oh, okay, so it's DDV. Started with the core file. I'm not like debugging the live session. I'm debugging what happened. So this is like forensics. So I can get a backtrace of where it crashed. So I can see exactly where the crash happened. So I was in main called unsafe function. Now that's my name, just so I know that this is a demo, right?
Yeah.
And then here's the string input string. So remember I said it's a pointer? So that's the value of the pointer. And this is this memory I'm pointing to. blah, 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 blah. And then right here, it tells me the line number. And then you see this underscore underscore stack check fail. That's the probes that the compiler put in to the checking.
I suspect my phone only has 3 more minutes of memory to record to.
I'll
So-
try to talk fast. Well, good, we can turn off and then be honest. So I'll turn off, there's the stack protector, I'll turn that off. That's usually an option if you turn off warnings. So evil. Oh!
Doesn't like the
Oh, it doesn't like the
semicolons.
semicolons, sorry. It thinks those are, yeah. Yeah, oh, I gotta do it without semicolons. I should have used that trick I showed you earlier. About the number of letters, huh? Oh, there we go. So in this case, we got a core dump, but it wasn't a stack protection core dump. In this case, I just overrode memory, or we just went off into la-la land. So what happens is the hackers need to find a way to, because normally this will happen if you overwrite memory. It would just go off into a random location and then run an invalid opcode. But if you do it just right, and you get around all the workarounds, you can actually get it to run code. And if you want to see some actual examples, Google smashing the stack for fun and profit. So this is the